Welcome to this explainer. Today, we're unpacking a fundamental mechanism of our modern world. Whether it's the phone in your pocket, your desktop computer, or the massive servers powering the internet, everything, from high-resolution photos to complex software applications, is fundamentally built on just two states, 0 and 1. In this session, we are going to explore exactly why that is. Now, it's a completely natural question to ask. When we look at advanced modern technology, it seems almost counterintuitive that it relies on something so seemingly restrictive. Why not just use the versatile 10-digit system we use every single day? Surely, a system utilizing the numbers 0 through 9 would be far more efficient for storing data. Well, the answer to that question fundamentally shifts how we need to view our devices. You see, computers use binary not because it is mathematically elegant, but because it is the only system that functions reliably in the physical world. Section 1. The binary foundation. Before we explore the physical hardware, let's briefly clarify what binary actually is. Binary simply counts in powers of 2 rather than tens. So instead of ones, tens, hundreds, and thousands, we have 1, 2, 4, 8, 16, and so on. This means a standard number like 13 translates into the sequence 1101. It looks a bit strange to our human eyes, but it represents the exact same mathematical value. And at the lowest level, computers use this two-state system for absolutely everything. A letter on your screen becomes a specific binary code. A single pixel in a photograph is assigned binary values to dictate its color. Even complex music and video are really just massive streams of binary data changing over time. Section 2. The physics of hardware. Let's dive into the core physics problem that makes this binary translation an absolute necessity for our machines. Inside any computing device, data isn't being processed by some abstract digital brain. It's processed by physical components, specifically billions of tiny physical switches called transistors. Because of the strict laws of electronic engineering, a transistor can really only do one simple thing reliably. It can be on or it can be off. On is a 1, off is a 0. Trying to store 10 different voltage levels in hardware to represent the numbers 0 to 9 might sound incredibly efficient. You could theoretically process more information with fewer switches. But as it turns out, that idea completely ignores the chaotic nature of real-world electricity. Because in reality, electricity constantly fluctuates. Components generate heat, there's background electrical noise, and there's interference from other parts of the system. If you try to run a tightly packed 10-level system, small fluctuations would easily cause the computer to confuse one value for another. A tiny bit of heat, and suddenly a 3 is read as a 4. In computing, that leads to catastrophic mistakes. And this is why binary is so remarkably practical. By relying on just two states, a low voltage and a high voltage, binary provides a massive safety margin. Even if the signal shifts slightly due to heat or noise, the system doesn't get confused. It can accurately read the signal and definitively say, this is absolutely a 0, or this is absolutely a 1. Section 3. Why decimal computers failed. To truly understand why this matters, we only need to look back at what happened when early engineers tried to ignore these exact constraints. The very first computers did not all default to binary. Several pioneering machines actually attempted to operate using decimal systems, trying to physically represent 0 through 9 right there within their circuits. But those attempts ultimately failed, because handling multiple electrical states was just far too complex for the hardware. These decimal machines ended up being massive, remarkably sluggish, and incredibly prone to constant failure. Simpler circuits meant vastly fewer errors, which made binary the clear path forward. Section 4. Thinking through logic gates. Knowing that simpler circuits are better, let's explore how binary scales up to actually perform complex tasks. It helps to remember that computers don't actually understand anything about the tasks they are doing. They simply route reliable binary signals through millions of microscopic pathways known as logic gates. A logic gate is just a tiny circuit that processes binary using incredibly simple rules. You can think of these gates as physical toll booths strictly directing electrical traffic. They follow basic logic. An AND gate only outputs a 1 if both of its inputs are 1s. An OR gate outputs a 1 if at least one input is a 1, and a NOT gate just flips a 0 to a 1. The sheer power comes from scale. By combining millions or even billions of these simple logic gates, the machine builds up from those basic rules to doing math. That math allows it to run complex programs, render stunning visual graphics, and execute massive decision trees. Section 5. The invisible impact. This seamless marriage of basic rules and physical hardware has heavily driven the scaling of modern technology. Consider the evolution from room-sized computers to modern pocket-sized devices. Because transistors only have to do the remarkably simple job of reading a 0 or a 1, they can switch states incredibly fast. And more importantly, engineers can shrink them down to microscopic sizes, safely packing billions of them into the tiny smartphones we rely on today. However, to be completely thorough, this physical constraint does come with hidden limitations. Binary isn't entirely perfect for all human math. For instance, a simple decimal value like 0.1 cannot be perfectly stored in binary fractions. This leads to tiny, almost microscopic rounding errors buried deep within complex calculations that computer scientists have to actively manage. But ultimately, computers use binary because it perfectly matches the real-world behavior of physical hardware. It turns countless yes or no physical decisions into the reliable foundation of everything, from basic tools to artificial intelligence. Extreme simplicity really is the foundation of extreme power. Which leaves us with a fascinating question to consider. How might the entire future of computing evolve if we ever manage to engineer a perfectly stable physical system that goes beyond just 0 and 1? Thank you for joining me for this explainer.